Okay, good afternoon, everyone. We're back to continue with our lecture on support vector machine. So last time we did our first example on how to compute a support vector machine that is linear. Okay, there were some things that I didn't explain in detail about certain characteristics of that simple linearly separable data, where in that case we say that our function or the kernel function is trivial, or the phi is trivial. That is normally the case when your data is linearly separable. Okay, now let me share my screen. Then we can. Okay, this was the example that we had. And let me say this. Okay, so this was the example that we discussed from last meeting. We are saying that for linearly separable data, the phi, or the function that maps the input space into the feature space is, or the kernel, sometimes people are calling it kernel, is trivial. So why is it trivial? Well, to say that what is the input, first we define what is the input space and what is the feature space. Okay, the input space, for example, in this case here, we have these dots. Okay, the blue dots to the left and the red dots to the right. I mean the red squares to the right. Okay, and in this case they are separated by this yellow region. Okay, the input space is where these inputs, our inputs are these things here. These dots are our inputs. So in this case, 1, 1 is an input. Yeah, 1, 1. This is 2, 1. 2. This is 2 minus 1. This 1 minus 1, and so on. Those are our inputs. Okay, and so in this case, this is the input space. Okay, then what is the feature space? The feature space is normally where you bring your data or your input data into another space where you classify them. Okay, so normally what happens to SVM is that you bring, for nonlinear separable data, you bring it to another space. We call it a feature space. So where you will try to separate them to classify the data linearly. Okay, so never mind. Let's just keep that one in mind. For now, we say that for a case of a linearly separable data, so what is a linearly separable data? That means that we can have a line. Okay, we can draw a line to separate the two. Okay, the two groups of information, or two groups of input data. So in this case here, we are saying that for linearly separable data, okay, your phi or your mapping is trivial because your input space is the same as the feature space. Meaning to say, when you plot their data into the input space, the same information is where, the same space is where you are going to classify them. Okay, you don't need to bring it to another space, to another feature space. This is the input space. This is where we're going to classify them as well. So in that case here, your phi is trivial because your input space is equal to your feature space. So your input space is where you classify them. Okay, so that means that your function does not do anything. Whatever your input is, it becomes your output. I mean, it doesn't process anything. Your input is not processed or anything. It's just whatever you give it, it will also output. You understand? Okay. Okay. I really think that Olefa, Mr. Chepo, I think you're looking at something. Okay, can you repeat what I'm saying? Come on, you're looking at something down there. You're not looking at the screen, at your screen. Can you repeat what I'm saying? Why is it in this case the phi or the kernel function is trivial? Why do we say that the kernel function is trivial, or the mapping of the transformation data of the input space into the feature space is trivial? Hmm? You keep your eyes on the screen. Okay, say something. Just say something. Why? Why is the phi trivial? Come on.
I don't know.
You don't know.
Yeah.
Okay. You can just tell me what you were doing so that we will know what you were doing.
I just forget.
Okay. You were not listening, yeah? Okay. Let me say one more time. Okay. Then we say that it is trivial because your input space, okay, input space is where you plot our data. These are inputs, okay? Feature space is where you classify them. In our case here, because the data is linearly separable, our input space is the same as the feature space. That means we plot them, we plot our inputs. That is where we are going to separate them also. Feature space is where you classify them, is where you separate your data. Okay, so in this case, this is the feature space. This is also our input space. They're the same. The input space and the feature space are the same. And so the function does not do anything. Whatever you give it, it outputs the data as it is. That's why it is trivial. Okay, can you say it in your own words, Mr. Olefa?
Our input space is the same as our future space. So we will just input the same output, the same data.
And so
it is trivial.
and so your phi function, the mapping function is what?
Mine?
The mapping function is trivial. Okay.
Yeah, the function is trivial.
Okay. You look at the screen when you are discussing. Okay. So I guess everyone understood that one already. And so from last time, our example, because we're considering the bias, we augment the input with our bias. And so this is a two-dimensional space. We already know that to include the bias information, we add it as the last component of our data. And so here you have we consider the only, okay, I should emphasize that the equations that we are using here are already the equations that we derive in terms of optimizing support vector machines. And so these equations, okay, give us information that whenever we use this, whatever the output of the W is from these computations will be our optimal W that will give us the correct classification. Okay, so we apply these equations. And so in this case here, we start with using our support vector machine. So using the support vectors. We use the support vectors in this form and compute for alpha. And then once we know the alpha, then we will multiply it with the support vector to compute your W. Okay, so that one we understand. So now let's go back here. So we mentioned that in order for us to consider the bias and not have this W as a separate to our X, we put the the B as part of our X. We put our B as the last component, okay, to the X. And so your W will be W, X as 1, and then your W will be, you have a B here, okay, as the last component for the weights, so that when you multiply, it will come out in this form, okay? So our X's here, or our inputs, will be augmented with 1, okay? So now we only consider the support vectors. So this is the support vectors for the classification of 1, and support vectors for the classification of -1, I think. Okay, we will see later. So now we say that this is, what is this? 2, 1. So that's 2, 1, and this is 2 minus 1, and this is 4, 0. So we augment this with a bias 1 for your support vectors. So if we consider only in our equation, in our equations that we are computing, we only consider the support vectors. Okay, we don't need to compute the rest. This one we don't need, this one we don't need, that one we don't need, this one we don't need, that one we don't need. We only use the support vectors. Okay, because we only need to compute for the W, and the W is enough. The weights is enough. The information of the support vectors is enough to compute for the W's. Okay, so now we take the support vectors here and we augment them. So we use these equations, which were already derived from the optimization equations that we discussed in class previously. These equations here, okay, these are this is the equation resulting into this, okay, into this alpha times the output times the X, and so on, okay, and so on. And this one is also, I think, alpha times, I don't know, where is the equation for the W? This is one equation. Okay, anyway, so we can go through, we don't need to trace the derivation, but we will use the equations that are given to us, because these equations are the result of those optimization process. So now we will use this to compute for the weights, or we consider to compute for all the X's, for all the inputs, or we consider only the support vectors. In this case, we compute the support vector here and the support vector here. Okay, now let's consider this equation. So in this equation, hold on. Hello, Mr. Messi. I'm in a class. Oh. Call me later. All right. Okay. So now, in this case here, we have, okay, this is the negative. Okay. So this classification is the negative classification, -1. And this classification is the +1. Okay. So now we will compute that equation, this one. So we have alpha I SI times the SJ. Okay, now, so that equation, let's just write it down, plus -1. Okay, depending on the classification, is the sum of alpha I SI from I to how many, to M, so how many support vectors are there, okay, times SJ, where your SJ is the support vector that is the constant. Okay, so now, so we will just follow. So if you have S1, so alpha 1 S1 times S1 plus alpha 2 S2 times S1, alpha 3 like that, and so on. So these are the augmented support vectors already. And the classification of this is the same. This one is the classification of this support vector. So the corresponding classification of that support vector is that one. So because this support vector is -1, so that's -1. Okay. So again, we consider all the support vectors now on the second support vector. So we consider everything the same here, but on the second support vector times S2. And again, your S2 is -1 classification. So this is -1. Okay. On the third support vector, we consider, because this one, you go through all the support vectors alpha I, Si, multiplied by the constant support vector. So now this is one support vector constant. And then this one is the classification of this support vector. This is +1. Okay, so I guess that is straightforward. And then all we need to do is, now again, I want to emphasize that we are using these equations because, okay, our phi is trivial. If it was not trivial, then we are going to do something else. What we are going to do is that we are going to transform the input space into another space before we classify our data. Okay, so for now, our input space is our feature space, so we classify it in here. So these are the corresponding equations. And so these are your support vectors. So we just substitute. So we substitute everything here, substitute all those values of S1, S2, S3 multiplied by S1. Okay, so S1, S1, S2, S3, and this is all multiplied by S1, all multiplied by S2. This is S2, and then all multiplied by S3. You see, this is S3 times S3, they are the same, and S2 times S2, they're the same, and S1 times S1, they're the same. Okay, so you multiply it, you just substitute the values, and then that's it. Then we get these 3 equations and 3 unknowns. Okay, that's a solvable one. So we can either just, just do a substitution, or we can do inverse of this one. You can create a matrix and you take the inverse to compute for alpha 1, alpha 2, and alpha 3. So now, this equation, the first classification equation using the summation of the support vectors of alpha I and Si multiplied by Sj. This equation gives us the value of alpha. Okay, so once we know the value of alpha, then we will use another equation to compute now our W. So our W is alpha I times Si. Okay, summation. Okay, those are the equations that we do here. Okay, there. Alpha I times Si. So we make use of this equation first to compute for alpha I, and given all the support vectors. And after that, we know the support vectors, we know the alpha already, then we can compute for W. So once we know the alpha already, now we can compute for W, just substitute into the equation, summation of alpha I times Si. So substitute all those values, alpha I, then you get your W. And so your W is W1, W2, and this is B. Okay, because we are using augmented support vectors, the last part here is the B. So now we can say that your W is 1, 0, and your offset is -3. So that means that if you have X1, so you have W transpose times X plus whatever B. So because W is 1 and 0 times X1, X2 plus, in this case, -3 is the classification. is the classification Y. Okay, now let's check. Okay, now, so if that is the case, then we always have x1 here, so x2 does not matter. X1 minus 3 is equal to the classification Y. Who's that? Okay, so let's check. So given this S1, X1, let's just say we take the support vector. So what is X1 here? It's 2, right? We don't consider X2 because X2 is multiplied by 0. Sipa. Okay, I will mute you. How do I mute Sipa? Okay, let me mute him. Mute audio. It doesn't work. There. Okay, so Japan is muted now. That's better. Okay, now let's go back. Okay, so where were we? We had so we know that our W is like that. So W transpose times X plus B is equal to your Y, where your Y is your classification. So your Y can be, if you're in this side, that means that what? This side, your Y is what? Okay, less than 0, okay, negative. And that side, okay, this side, your Y is what? Greater than or equal to 0. Okay, so now, so in this case here, it should be, when you're in the support, okay, support vectors, it should be -1. Okay, here, support vector, it should be +1. Okay, or greater, +1 or greater, -1 or greater. Okay, if there are points here in between, it will be somewhere between 0 and 1. Some points here in between this separation line or the hyperplane with the support vector, the value should be between 0 and -1. Okay, so now we are saying that your W is 1 and 0. So that is 1, 0, okay, multiplied by x1, x2. -3. Okay, let's just write it again. Is equal to the Y output. So now this is x1 minus 3 is your Y. So let's start with the support vector. So what is x1? So remember, this is the axis of x1, okay? So if we start consider just a support vector, so this is 2, yeah? So 2 minus 3, that's a -1. So this is -1. Again, this is 2 minus 3, that's also -1. What about this 1? 1, so in this point, 1 minus 3, that's a -2. And the same thing here, this is a -2. Okay, so what about this one? This is 4 minus 3, that's a +1. And then 5 minus 3, that's a +2. +2, +2. 6 minus 3, that's a +3. Okay, there you go. So we look at these classifications. This is greater than 1, greater than or equal to 1 for these points. So here, if you look at the classification, this is less than or equal, less than -1. Okay, so as you go here, it becomes bigger, negative number. As you go, it becomes bigger, positive number. Any questions? So in this case here, our feature space is the same as the input space. We classify them into the input space, okay? And then because the data can be separated linearly, Okay, later we will discuss about data that cannot be separated linearly, and so we have to change. We have to consider, bring the data, transform the data into the feature space. Any questions? No questions, so let's continue. Okay, so now in this case, this is a non-trivial case where your fee, again, let's write down, I should emphasize that your feature space, fee, your feature space output is your function, transformation function from the input space. So the input space you transform with this kernel function and then equal to the feature space. Okay, so we normally do that if the data are not linearly separable. So just like in this case, this me, your red squares are inside this circle, and then your blue triangles are there. Okay, there's no way we can separate them linearly. If you draw a line here, no, they're not separated linearly. Even here, okay, there's no way we can separate them linearly. Okay, no matter how we draw the lines, we cannot separate them linearly. So that, then we say that yes, this data, excuse me, is not linearly separable. So because it is not linearly separable, now the point is we bring the data into the feature space into another space. We transform our input space into another space, okay, in such a way that in that feature space, when we go to that feature space, now we can separate them linearly into that space. Okay, so the purpose here is here we cannot separate linearly, but if we transform this into another space, probably there is another space where your red squares will be somewhere, okay, like that. We transform them, and then when we transform them, your blue triangles will be here. Okay, maybe like that. Okay, if that is the case, then we are okay. We can linearly separate them. Okay, so now the question is, how do we know that transformation function that will bring our data into a feature space where we can linearly separate them? Okay, that's the biggest challenge for SVM. We need to think of a function that will transform our input space into a feature space, into another space that will transform our data, our non-linearly separable data, into a linearly separable data. Okay, so the question now is, how do we formulate this function phi? Okay, so let's continue. So we apply. In this case, our input data is this. So the red dots are -1, so this negative. So we write down, this is 1, 1, that's 1, 1. This is 1 and -1, that's correct. That's 1, 1, 1, -1, -1, -1, and -1, 1. Okay, these are your red squares. And now your blue, this is just the input space, okay? We are getting there. Coordinates into the input space. Okay, now we get the blue triangle. So 2, 2, that's that one. 2 minus 2, minus 2, and minus 2, 2. Okay, so we can say that it looks like we multiply everything by 2 so that you will get into the blue triangles. Okay, so now that is your input space. Now we say that for feature space, okay, we propose this transformation, this feature space transformation function that will transform our input x1, x2 into some values into the feature space. Okay, so what is that? So we say that, well, we say that if x1 and x2 is greater than or equal to 2, the square root of that, okay, if we take the, it's like the norm is greater than 2, then we compute this as our feature space. Then if not, if the norm is less than 1, then we just retain the original value. Okay, so the purpose then is that we need to, what is this purpose? So the purpose there is that we need to keep those data points that are less than this, the norm is 1, okay, these red boxes into the same space, and those the one outside, we bring them somewhere so that they will, it's like they're being thrown. They're always positive. The things become always positive. So they are always in this quadrant, always in that quadrant, and big and bigger. Okay, so now if we, so x1, okay, x1 minus x2 absolute. So what was the first value? This one is the input space. For example, okay, let's do 2, 2. So 2, 2, this is x1, x, that's 0. Okay, so that is 0. And then here, this is x2, 2, 4 minus 2, that's a 2. So now the first value x1, that is x1. And this is x2. Okay, so x1 is 2, that's that one. So again, 2, 2, you're taking the positive value. So 2, 2, that's 0, and then 4 minus 2, that's a 2. So it is there, 2, 2. This is that one. Okay, so in terms of feature space, it remains there. Okay, so that 2, 2 becomes like that because of that equation. So now for 2 minus 2, so 2 minus 2, so minus negative. So 2 minus negative, that's a 4. Okay, so this number is 4 always. So minus x2, so minus x2. Okay, minus x2 minus 2, so that means positive 2. So 4 plus 2, that's 6 plus 1, 10. Is that correct? I mean plus 4, 10. 4, this is minus 2, right? So 4 minus 2. So what is that? 6. Okay, plus 4. It's supposed to be 10. How come that's 6? It's 10. That is wrong. Yeah, this is 10. There's no 6 here. So, okay, hold on. Which one we should be? Which one is 10? So let's check. Okay, if this is x2, okay, we were considering this one. I think this is a 10. Let me check first. So if we go here, this is 2 minus 2. That's a 2 minus negative 2. Still, that's a 4. And then this is 2. So 4 minus 2, that's a 2. So this is what? 2 plus 4, that's a 6. So it should be this one, 10. Okay, never mind. Don't change that one. Okay, this should be 10 and 6. Okay, so where is 10 and 6? This is 10 and 6. So that is 10 and 6. This one. Okay, we're coming from that input space and this input space. Okay, we transform them now into from 2 to this one does not change much. From 2 and minus 2, it becomes 10 and 6. So that's 10 and 6. Okay, I have to correct this one. Next, what is this now? you have minus 2 and 2. So let's erase this. Ah, okay, sorry. So this one remains x1, x2. Okay, so minus 2 and 2. So minus 2 minus minus 2. Okay, so they're the same sign. So what does it mean? Minus 2 minus minus 2. So minus 2 plus 2, that's a 0. Yeah, so that's a 0. And this one is also a 0. So now what is your x2? 4 minus minus 2. So that is a 6 and a 6. So that's a 6 and a 6. So this is correct. So in this case here, that's 6 and 6. So that means that this point here is that one, okay, coming from this one. Okay, so the minus 2 becomes 6, 6. Now for minus 2 and 2, let's erase. Okay, so if you are minus 2 and 2, so minus 2 minus 2, so minus 4. So because absolute value, that's a 4, and this is a 4. So 4 minus minus 2. Okay, that means 4 plus 2 is 6, and then 10. So this is 10. This is wrong. Is it correct? And then 4, sorry. This is x2. So this one. So 4 minus 2, that's a 2. Okay. Plus 4, it should be 6. Okay, let me check again. So minus 2 and 2. Minus 2 and 2. Minus 2 minus 2, that's a minus 4. And then absolute value, that's 4 all the time. So now x2, 4 minus 2, that's a 2 plus 4, it should be 6. That's correct now. Then now 2, so this is 4, but 4 minus 2, that's a x1. 4 minus minus 2, okay, that's a plus 6. Okay, so that means 6 plus 4, that's a 10. So this is 10. 6 and 10. So this is the one. 6 and 10. So 6 and 10 is this. Coming from this one. Okay. So now that is how we transform our input space into a feature space. Okay. So and then we say that for the data, that is the norm is less than 2. Okay. So for sure here the norm here is less than 2 because it's 1 squared plus 1 squared, 2 square root of 2. What is square root of 2? 0.707, I think. So that is less than, okay, I think that's correct, 0.7. And so that is less than 2. And so here, for those input data, nothing is changing. So in this case, if that is the data, our transformation matrix, transformation function is trivial. So we keep the input space as our feature space. Okay, so now, again, we're saying that here, we can separate them now linearly. Okay, so if that is the case, then where is our support vectors? Where are our support vectors? So this is one support vector that's closest to that plane, another support vector that is that one. So you have two support vectors here. Understand? Okay. So from those support vectors, then we apply those equations that we have previously derived. Now you have two support vectors. So our support vector 1 is 1, 1, and this is 1, 1, and 2, 2. Yeah. And now we do our alpha, this one, alpha times the phi of the support vector, okay, and multiplied by the support vector 1 and support vector 1, and then alpha 2 support vector 2, alpha and times support vector 1. Okay, the only difference here is that you apply alpha now, the alpha function, into the support vectors. That means that you transform them into the feature space. Okay, our support vector is 1, 1. Okay, that is this is 1, 1, and then the other support vector is 2, 2. Okay, so now if we transform them into the feature space, then we can say that this is your okay, we transform them into the feature space. And so how do we do that? What will be the value of S1 and S2? What is your value of V? Okay, if it's less than the norm of 2, okay, so definitely this one, we don't apply the feature transformation, because we only apply the features transformation when your norm is greater than 2. Okay, so what about this one? The norm is greater than 2. 2 squared plus 2 squared. Okay, square root of that. I think that's greater than 2. Okay, 4 plus 4, 8, greater than square root of 8. Okay, okay, that is greater than 2, because square root of 4 is 2 already, then square root of 8 must be greater than 2. Okay, so then we have to apply that transformation function. So the transformation function is this one, 4 minus x2, okay, 4 minus x1 plus the negative plus the absolute value. So here you have, okay, so the transformation for x1 is equal to 4 minus x2 plus x1 minus x2. Okay, the other one for x2 is 4 minus x1 plus x1 minus x2. So if your value is 2, 2, so here we apply this 2, 2, so that's 2 and 2, so this becomes 0. That becomes 0. And now, what is this value? When you transform it into this transformation space, so what is that value? 4 minus 2, that's a 2, and 4 minus 2, it remains a 2. Okay, so here the support vector is that value here remains 1, 1, because okay, that is not applied with the transformation function, because the norm is less than 2. Here, the S2 remains the same also. It becomes 2, 2, because by this computation. So here, this is 1, 1, 1, 1, and 2, 2, 2, 2. So now, okay, if you compute, can you please compute if these are the correct values? So you have, where can I write here? So this is 1, 1 transpose multiplied by 1, 1. Okay, and this is 2, 2 transpose multiplied by 1, 1. What is that? So this is 2 alpha 1. What is this now? 2 alpha 1 plus, if that is 2, 2, this is 4. 4, but there, this is a 5. This is 3 plus 5. What happens? What happens? Lucky, I have a class, Lucky.
Oh, you have a class.
Yes, yes.
Okay.
Okay. What happens here? There's a missing one. Okay. If you remember, this information here is the augmented support vectors already. Okay. So that means that after you transform them into the feature space, then you augment it by one. Okay. So okay. So we have seen here that you transform when you transform S1 into the that alpha, so your 1 1 will remain as 1 1 when you transform, and the same thing as your 2 2. Fortunately, 2 2 transform into, you apply the phi, it becomes a 2 2. Okay, it's like nothing is being done, and then you augment it with this tilde. You augment it, so that means it becomes 1 1 1 1 1 1, and this becomes 2 2 1. Okay, so here 1 1 1 comes 2 2 1. Okay, transpose 1 1 1. Okay, so it's correct now. So this is 1 plus 1 plus 1, that's 3. 3 alpha 1, that's correct. 2 plus 2, that's 4 plus 1, 5. 5 alpha 2, and this is minus 1. Okay, so next, again, you have 1 1 1 multiplied by 2. So this is 5. 5 alpha 1, and then this is 2 2 1. And this is 2 2 1. So it's just 2 times 2, 4, plus another 4, that's 8, plus 1, 9 there. So this is correct. Okay, so 2 equations, 2 unknowns, then your alpha is this. Okay, you can compute for your alpha. So what is your weights then? So we apply the weights. So where do you think we will apply the weights? Do we apply it in the feature space or into the input space? Where? Remember, there's one information here that was not clearly stated. You apply the transformation of the input space into the feature space on not the augmented support vectors. You augment it after you have already transformed into the feature space. Why? Because you classify your data into the feature space. That's when you will have your B, or that's when you will have your offset. So the B augmentation will be into the feature space. That means that your weights also that you will compute will be applied into the feature space. Well, that is logical because that's where we apply the linear classification of the input data. Okay, that was not linearly separable. We transform them into the feature space now where they can be linearly separated. Okay, so if you move, continue there. Now you compute. We know that your weights is to compute for the weights. This alpha I times SI, where your alpha we have computed it to be -7 and 4, -7 and 4, and these are your support vectors. Okay, so now your W is 1 1 and your B is -3. Okay, and when you classify each one, you apply the classification, then you will know. Okay, we will discuss this one later because there are some computations here that will help us classify. Okay, so you classify them, and then we will understand how this how the classification becomes linearly classified, and then what we will do this, what will be judged or what will be output in terms of the input space that was already or originally given to us. But for now, we see that now in the feature space, we're able to classify our newly transformed data into the feature space into linearly separable data. Now, this line, this equation of the line W11 and B3 minus 1, that means that if you apply it in the equation, it will be x1 plus x2 minus 3 will be equal to y. Okay, that is your linear equation that classifies your data. Okay, we will check this one when we come back. Okay, let's have a 10-minute break. Before that, any questions?